and Renewable Energy, IIT Roorkee. He did his postdoctoral fellowship from Georgia Tech, Atlanta. He did his PhD from IIT Bombay and Monash University, Australia in 2017. He did his graduation from BITS Pilani. He published more than 25 research papers in various national and international journals. He got various awards. One of them, that is a Bioenergy Award for Cutting Edge Research, fellowship by Indo-US Science and Technology Forum. He got the Best Collaboration Oscar Award in 2014 at the annual IIT Bombay Monash Research Academy Oscar Award event. He also got, that is the first number in Utkarsh held in TechFest 2012-13 in IIT Bombay for presenting on a low-cost water purification technology based on ceramic water filter. He also achieved a Merit Cum Need scholarship by BITS Pilani. Welcome, Arora sir.
Thank you, Professor Ronak, for the nice introduction. Should I begin my talk?
Yes, sir.
Okay. So good afternoon, everyone. I believe you are having a good time in this course, and you have learned about many renewable energy technologies. So today I will be taking through briefly about my research and production of sustainable chemicals, and I'll be focusing on ammonia, which is one of the major chemicals that is produced in the world through a biomass source, and using different modeling simulation studies as well as circular economy approach.
Sorry, sir.
So I would request, yeah. So
for your presentation slide is not seen.
Yeah, yes, I'm just sharing that. So let me know if my slides are visible to everyone.
Yes, sir.
Okay, let me do it. Okay.
Okay.
Yeah. So feel free to interrupt me in case you have any doubts, or if the slides are stuck, or if my voice is not audible at your end, because these are the normal things that we experience in the online lectures. So I'll begin my talk. So the talk is entitled Biomass-Based Green Chemicals, the Circular Economy Approach. So I'll be taking through different steps or different modeling studies which have been done for attaining this. And I have a different presentation based on LG, which I can take out, also present if the time is left. But as of now, let me focus on this. So the outline of the talk would be divided into an introduction, modeling of a gasifier, which is a bioenergy process, then a model for the biomass to ammonia process, some basics of life cycle assessment, then multi-objective optimization for optimizing both the emissions as well as the economics, results and conclusions. Again, another brief summary of what I'll be taking you through is like, are the slides visible? Are they moving at the end?
Yes, sir.
Okay, great. Okay, so I'll be taking through different modeling and simulation exercises at 4 different levels. The first one would be at a phase level, where I'll show you some CFD simulations. The second one would be at the process unit level, where we'll try to model the gasifier and use it for different biomass feedstocks. The third one would be at plant level, where the whole ammonia production from biomass is modeled. And finally, the life cycle assessment, which is more also on a national or a global level. So this would be the approach that we will take in this study. So yeah, again, the talk is entitled Production of Sustainable Chemicals. and there are many chemicals, and we'll be aiming for one of them, which is ammonia. So why ammonia? Few facts. Annual production 131 million tons, 6th most produced chemical in the world. Just to give you a preview, like most of the fertilizers that you are using in the fields, basically urea are coming from ammonia. And this ammonia is based or produced from natural gas or naphtha, which are fossil sources. So it's consuming a lot of amount of primary energy of the world, as well as it is also contributing to the greenhouse gas emissions. We are burning those fossil fuels to derive hydrogen, which serves as the source of hydrogen in NH3. Ammonia is NH3. So the hydrogen is coming from the combustion of coal, and the nitrogen is coming from air. What happens to the carbon in the fossil fuel? It is vented to the atmosphere. So that's why it is losing all carbon to the atmosphere. And that's why it's a burden. You can't like live without it because your food supply is based on it. But you can't avoid it, because if you avoid it, the production of the field goes down and we have a huge population to feed. How are we going to achieve that? So the only alternative to that is, why not search for a green source for producing this chemical, which is ammonia. So next, can biomass be a potential feedstock for this? Now, biomass is widely available and it is carbon neutral, because any emissions that you cause by the use of biomass or through the burning of biomass are recycled again through the growth of biomass in due course of time. The same can be said for the fossil fuels as well, like coal or natural gas. They would be produced in due course of time, but their due course of time would be of the order of millions of years. Whereas for biomass, it could be as low as 20 to 30 years. So that's why biomass is said to be carbon neutral. It has a very low shelf life in terms of the CO2 emissions. The emissions that you cause now by the burning or the use of biomass will be recycled in another 20 years. So the life cycle of the CO2 is very small. Whereas if you compare this with the different fossil fuels, it would be spanning over millions of years. But biomass, like other fossil fuels, has a low energy density. The reason being, biomass has a huge amount of oxygen. A typical biomass would have around 50% oxygen, whereas this quantity is only 5 to 6% in coal. So the efficiency is almost reduced by 50% as compared to other fuels like coal or petroleum, which hardly have any oxygen. Thus, it also decreases the density. A decrease in density means a huge transportation cost. Also, biomass is not available all the time. It's restricted by seasons. You have certain farm base which are available only after the harvest of the crops. The wood can only be harvested on that particular time. Like the monsoon season is going or just ended, you can't harvest any wood at this time because it would have a huge amount of moisture. So it has its own problems. And ammonia production generally takes place at a very high scale, at 1,000 tons per day or 2,000 tons per day, to help to gain the help from the economies of a scale. If you have a larger production of any chemical, the price goes down. That's why it's always good to have big factories, because you can like we get the advantage of economies of scale. But that can't be done with the biomass. So this study aimed at a low-scale biomass plant which produced ammonia at 20,000 tons per year, or it could be around 70 tons per day, which is very small as compared to 1,000 tons a day capacity of conventional ammonia plants. And to avoid any food versus fuel conflict, now people may say, like, if are you going to grow biomass in the fields, where are we going to grow our like rice and wheat? Like, we have a huge population to feed. So we are just aiming for second generation biomass feedstock, which includes trees like eucalyptus or the rice straw, which has been burning in the field, or bagasse, which don't have any food value. So they are called second generation biomass feedstocks. And our study will focus on these types of feedstocks. Second, but there are some added advantages as well. If any one of you is from North India, they might have experienced this smog in the months of October and November. I believe it's going to start again soon in the coming days. And this is nothing but majorly attributed to the burning of the straw in the rice fields. And the farmers are also helpless. They have just 15 days time to extract the waste from the field and plant a new crop. They don't have enough money to collect the feedstocks that are spread on the field. So the best way they can do it is just burn it. And this like makes the task easy, helps in their soil, but causes pollution throughout the northern India. The second part is something peculiar that we notice in countries like which have huge deserts like Australia. Herein you can see that salt is coming out of the earth. This is called dryland salinity because of the high water tables. The salt comes out of the land and it just renders the land useless for any purposes. And it could be made useful by planting of trees like eucalyptus, which consumes a lot of water. And by using water, they can help this solve this problem. So not only the problem of ammonia production, but we are also trying to solve the problem that are other associated, like something like pollution in the northern India as well as dryland salinity in Australia. So this study was done in collaboration with Monash University, which is in Australia. And also we had some Brazilian collaborators. So we thought, why not have 3 case studies focusing on 3 different places in the world? And if there are 3 different places, why not select 3 different biomasses as well? So we selected straw for India, eucalyptus for Australia, and bagasse for Brazil. Now, these biomasses are very different. Eucalyptus, if I say, is an energy crop. It's a dedicated energy crop, and it can only be grown in places which have large amount of land available. And Australia is such a country which has a very small population. The entire population of Australia is maybe less than the population of Mumbai. They have huge land, so they can plant trees like this. And also, like planting trees like this needs a lot of mechanization. A lot of equipments are needed for their nice plantation as well as cutting and harvesting. So Australia seems to be a nice location, and also they have this problem of dryland salinity, which can be taken care of in the plantations like eucalyptus or poplar. Okay. Sorry. Yeah, request everyone to keep their mics on mute. I would be happy to answer any questions that you may have. So feel free to ask them. But other than that, would request you to keep your mics on mute. Okay. The second biomass feedstock that we chose was straw for India. And the choice became conventional because this is one of the biomass feedstock that is causing a lot of danger, specifically in North India due to the smoke problem that we have here. Now, this is a farm residue. It's available freely, but it's scattered resource. You need a good amount of manpower for collecting it, and it's available in the field. It doesn't have any use per se. In some places in southern India, it's used as a cattle feed, but due to some other issues in North India, it can't be used as a feed. So it doesn't have any use per se. And the third one is a secondary residue. By secondary residue, I mean it's an industry waste. Straw is a primary residue because it's a farm waste. It's just produced and it's a waste available at the farm fields, scattered, and you need to collect it. Bagasse, on the other hand, is transported to the sugar mills. And just outside the sugar mills, you have huge quantity of bagasse just lying idle. You don't need to collect it, but it has some other uses. Like bagasse has been used for combustion as well as gasification, producing electricity as well. So it has some side uses as well. So reiterating again, now I have 3 different countries and 3 different biomass feedstocks: eucalyptus, straw, and bagasse. All the 3 are different types. One is woody, the other is a farm waste, and the third one is an industrial waste or a secondary residue. And third, all the 3 have different supply chains. It's not similar, like they have no similarity, whatever you say. And so the aim was to get, like, now we have enough diversity. We are looking at different countries. We are looking at different biomasses, and we are looking at different supply chains. And we are trying to see if we can produce ammonia from different aspects using biomass. So let's go further. Now, we chose a process which is called biomass gasification. By biomass gasification, I mean like you gasify or heat biomass in an insufficient supply of air. When you do that, what happens is biomass gets converted to gas called syngas or producer gas, depending upon the oxidizing agent. If you are providing in air, 50% of the gas is almost nitrogen and it's called producer gas. If you are giving in steam or oxygen, the output gas would be concentrated in carbon monoxide and hydrogen, and it's called syngas. And different types of gasifiers have been proposed at different levels of operation. So some of them have been listed in this figure. If some of you is coming from a mechanical background, they might be aware of this, or if anyone has been doing some research on biomass, these are different types of gasifiers that are available. And all of them are economical in different ranges of capacity. Like I begin with the downdraft to updraft, and the downdraft is like economical at very low scales, maybe 1 to 10 tons per day of biomass, and then train flow gasifiers are economical at very high scale, around 10,000 tons per day. The scale at which we were working, or which we were aiming, that was based on the ammonia production scale, was around 100 tons per day. And the gasifier which was most economical was the fluidized bed gasifiers. By fluidized bed gasifiers, I mean biomass is sieved or like cut into small parts, and it's entered into a bed which is subjected to a very high velocity of gases, such that the whole bed appears like a fluid. Let me show you in the next figure. So this is how the concept works. You have the biomass going in from the left side of the reactor, which is the biomass gasifier, and then you have the steam, which is acting as an oxidizing agent. So the steam is supplied at such a rate that the whole biomass, sorry for this, the whole biomass acts as, I don't know if you can see my cursor. Yeah, it acts as a fluid. So that's why the name fluidized bed is suggested. And what happens after that? As soon as the biomass and the steam react, the biomass gets converted into three things. One is the product gas, or the syngas, which goes of the reactor from the top. The second one is the char. It's something similar to charcoal, very rich in carbon, and that slides down and enters into a second reactor, which is called the riser. And in the riser, we have a supply of air. So with this air, the carbon burns in here. Burning of the carbon will heat the bed material. The bed material used here is silica or something similar to sand. That sand gets heated and it goes up. There's a cyclone up here which removes the carbon-rich gases, which is just nitrogen as well as carbon dioxide, and the heated silica or the bed material recycles back. So the heat for running or burning of the biomass is coming from two sources. One is the steam, and the other is burning of the char that is produced, and that char in turn heats up the bed material, which is the sand. So the hot sands get recycled, provides heat for the biomass gasification, and we have the syngas going from the top. The whole process doesn't have any oxygen entering into the product gas. So that's why the gas that we get is very rich in hydrogen as well as carbon monoxide. So this is what the gasification process that we will be modeling looks like. And it's called a dual fluidized bed gasifier because the fluidization is occurring at two beds. One is for the biomass and the other is occurring for the char. So that's it. There are two fluidized beds and they're combined together. It's very similar to the FCC cracker that you would see in a conventional petroleum refinery, if anyone you has done any research on crude refining. Okay, so let's start with the modeling of the gasifier. So multi-scale approach was used. So the gasifier that we chose was 8 megawatt gasifier that is running successfully in Austria since last 15 years or so. It is one of the success stories in gasification, which doesn't have much of success stories till date. So we adopted all the input data from that particular gasifier, which is available in open literature. And the first thing that we did was gasification is a dynamic process. It has a lot of variability with respect to the supply of biomass, oxygen, and the simulation that we were aiming was sort of steady state simulation. So we had to convert a dynamic system into a steady state system. How do we do that? So we did something called the RTD approach, which is called residence time distribution, or the tracer approach. We simulated the whole process or the fluidized bed process in ANSYS Fluent software. And once the simulation achieved a quasi steady state, what we did, we introduced a tracer at the input and noted down its concentration at the output. And the structure of the tracer or the concentration profile of this tracer at the output gave us hinting at the possible network of ideal reactors that could be used to replicate this dynamic system. Let me take you to more details. So this is what the typical fluidized bed looks like in a simulation. So probably you can see now the bubbles are almost equidistant on left and right side. But as time proceeds, the profile changes. So we can note down certain essential parameters and see when they stabilize, and that place we can say it's a quasi-steady state. And once we have achieved that, what we can do is we can introduce a tracer which doesn't have any reaction, which won't react with any of the components. It will just go with the velocity flows, something like this. You introduce a tracer and it goes along with the velocity profile of the current profiles, and you can note down the concentration at the end. You can see some of the tracer in the middle there. So this is how we did this in ANSYS Fluent software. And we took different approaches. Let me briefly mention the approaches. The first one is that we froze all the velocity profile and let the tracer go through. And we got a very simple tracer profile at the output. The second one is that is called the snapshot approach. We were changing the velocity profiles at every 2 seconds or 5 seconds. So these are the three profiles that I give at the changing snapshots, the one at 0.5 seconds, 2 seconds, and 5 seconds. But they also gave us very simplistic approach. The third one was a data sampling approach in which I'm averaging the velocity profiles over say 10 seconds and then doing a tracer analysis, similar results. And finally, I had to do a transient approach in which the velocity profile or the velocity equations are changing as in concurrence with the tracer equation. And this gave us the tracer profile which we aimed to replicate. And again, we noted down the tracer at different places. We noted it down just above the bed, at the middle of the bed, and the output of the bed. And this is the superimposition of the tracers at different levels, as well as the tracers at different places. And this also gave us a deep insight of the velocity profiles. On the right-hand side, I'll show you the velocity profile, how the gases look like at the different heights. And we could see like just above the bed, there is a wake formation. So either the gases are going from the left side or the right side. So there are two different chains of reactors that would be needed to model this thing. And the model that we came up with was something like this. Okay. So this part is basically a dense zone or the fluidized bed, which includes okay, so let me give you an understanding of the different ideal reactors as well. So there are two kinds of ideal reactors. One is called a plug flow reactor and the other is called the continuous stirred flow reactor. So any reactor that we might have could have a performance which is in between both of them. So they are the two kinds of ideal reactors, which replicate the ideal flows at the two ends of the conversion process. So any process can be, or any reactor can be modeled in the combination of these ideal reactors. It could be multiple PFRs or multiple CSTRs. So our aim was to model this dynamic process with the help of these ideal reactors, which are called PFRs or CSTRs. So we came up with this model. The first for the fluidized bed. Now, the fluidized bed has the bed rotating inside. So it should have a recycle. So we came up with the reactor size that it would have a CSTR with a recycle followed by a PFR. Now remember the middle that I showed you the two wake formations. So there were two different air profiles that were going in the two sides of the fluidized bed. So we need to model it using two different chains of reactors. One was a single CSTR and the other was two CSTRs in series preceded by a PFR. And finally, the top of the bed was where the velocity profiles have become subsided and it could be modeled by a single PFR. So this model is suggesting a CSTR and this is reflecting a PFR. And we also did a study where we are trying to match it with the standard equations using MATLAB, and we got a nice validation of our model as well. So this is how the reactor looked like. So it is the combined fluidized bed reactor, which I've shown in here, which have the dense zone as well as the syngas coming out and the char going to the combustion reactor, the char combusting, and the hot sand coming back, could be modeled something sort of this. And this was done in Aspen Plus software, which is again a very dynamic software, mostly used for chemical engineering processes, but now gaining a lot of importance in process systems engineering, specifically for biomass related simulations. So this is how we could model the whole biomass gasification process. It started with biomass coming in, then we have a small pyrolysis reactor which breaks down biomass into different components. Then the whole gasification process, we have the char and the tars leaving, it goes to the combustion chamber, gets heated, and the hot bed material gives back. So all the processes that occur in an actual process were replicated in the simulation in a steady state. So this was our first task, and that was fulfilled. And not only this, we did it for 3 feedstocks. Now remember, we had 3 feedstocks in the initial one. One was eucalyptus or wood, the other was straw, and the third one was bagasse. And we had a common input, which is 2.3 tons per hour, and the moisture content of around 27%. And based upon the characteristics of biomass, we had different composition of the gas of the same gas that we got. Like all of 3 of them had almost 40% gas or hydrogen and around 20% of CO. So again, we could validate this with the experimental values, and we came up with nice validation. So you can see different biomasses react differently. They produce gases of different composition, different types of tars, and as well as have different temperature profiles. You can see the temperature profiles varying. And they would also have the different amounts of bed circulation rate that we are needed. Like around, it also changes to maintain these temperature profiles. Again, we did a sensitivity analysis, and even that was found in validation with the open literature. We could found out the relationship like between the gas composition as well as temperature as well as the gas flow rate, and that was nicely validated. So once the model was ready, we wanted to go for ammonia production. Now, ammonia production is something that is a difficult process. Hydrogen comes from the burning of or the reforming of synthesis gas. So if any one of you remember the natural gas reforming, you might have done this in a school or college times. So that is the process of producing hydrogen, and that hydrogen is then combined with nitrogen to produce ammonia. So we try to do the same thing. We have the biomass. The biomass needs to be dried in case it has a lot of moisture. And then we have the dual bed gasifier. Now, the biomass or the syngas that we have has a good amount of methane in it, almost 10% that I show in here. So that needs to be reformed. So we need to have a reformer. So we had different configuration. In this file, I'm just showing you autothermal reformer. So once you have reforming, which occurs at around 800 degrees Celsius, we need to cool the gases. Then we need to compress the gases at around 20 to 30 bars because all the subsequent processes would occur at high pressure. Then we have a shift reactor. The shift reactor is basically conversion of carbon monoxide into carbon dioxide. Now, if I show you again, the gas has almost 20% of carbon monoxide. And if some of you look in the internet for the water gas shift reaction, it is nothing but CO combining with water, giving us CO2 plus hydrogen. So in a way, I'm converting carbon monoxide into hydrogen and like consuming some amount of water as well. So that's where the steam is going in. So after the isothermal shift, we need to go for a saturator or desaturator for removal of water. Then we need a PSA for removal of CO2 and also a methanation unit to remove any left around carbon monoxide or carbon dioxide, because these kinds of catalyst. Finally, we have another compression which compresses the gases to around 80 bars, and we have an ammonia synthesis loop which is occurring or running at a low pressure. Now you might be wondering like why I've highlighted some things. So these are certain aspects which we have taken from another plant, which was a small-scale ammonia plant. Now a normal plant wouldn't have these features. A normal plant would have a pressure loop that is occurring at 300 bars. We took it around 80 bars. They would have multiple shift reactors. We just took one of them. they would use a solvent-based CO2 removal. We used a PSA because all of them were cost-effective. And the reason why we said like this is the plant we adopted, which was a technology that came in around early 2000s for small-scale ammonia, but couldn't compete with large-scale ammonia plant because of certain factors. But as you can see, whereas normal plants achieved a minimum in cost at around 1500 or 1200 tons per day, these kinds of plants achieved a minimum in terms of economics at around 450 tons per day. So that's why we adopted these technologies. So in a sense, it was a novel combination of a new technology as well as an old technology. The old technology being ammonia production process, and the new technology being the dual fluidized gasifiers. So now we have three different configurations of the ammonia production process as well. And it was based upon how we are reforming the syngas. The first one had an autosomal reformer, which means I provide in the air. The air has nitrogen and oxygen. The oxygen is used to combust some amount of syngas, which would provide the heat, and the nitrogen provides for the nitrogen requirement for ammonia. Now remember, ammonia is two things, hydrogen and nitrogen, NH3. So the nitrogen is coming from here, and the hydrogen is coming from the gasification process as well as the shift reactor here. The second option is steam methane reforming, wherein I'm just providing in steam. So the advantage is that I don't need I can do it with a small reactor because everything now doesn't have any nitrogen till here. The nitrogen I can provide just before the ammonia loop through an air separation unit. But I need to provide the heat for the reaction, which would be taken from burning the fuel outside the reactor. The third one is a novel combination, which is called CO2 reforming or dry reforming. Why not use the flue gas from the combustion section of the gasifier? Now, the gasifier had two fluidized beds. One was producing syngas and the other was burning char, heating up the bed material, and the gases released was just nitrogen and CO2. So why don't you use that gas? That gas is coming at around 800, 900 degrees Celsius. You use that gas in this reactor. That will provide heat for this reaction, as well as it would provide in the nitrogen that is needed later on. So this was a novel combination that we proposed. Also, we need to do certain amount of heat integration. By heat integration, I mean we need to join different heat sources and heat sinks. There would be different places in the plant which would produce heat, something similar, like the shift reactors or the PSAs. And there will be certain parts of the plant which would require heat. So we need to combine them. And the strategy to combine them is called pinch analysis. We need to form a grand composite curve, something similar to that as formed in the figures below. And we automated that. So no matter what amount of steam or what amount of heat was available or it was needed, our plant was always running in an optimized fashion. We did it using Excel sheets and using an optimization algorithm. As you can see, the plant is running in two different configurations here. The first one is producing at around 8 megawatt of heat. The second one is around 6 megawatt of heat. But the steam production is always optimum. So this can be done with the use of pinch analysis. And finally, we did the process economics. So here I show you the ammonia production cost, which is in dollars per tons of ammonia for 9 different cases. We have 3 different biomasses and 3 different process configurations. The biomasses were wood or eucalyptus, straw, and bagasse. And the 3 configurations were ATR, SMR, and CR. So we can see that different biomasses have, and different supply chains have their different total economics or ammonia production cost. It is quite cheap to produce things in India because we have a lesser capital cost and a very low labor cost. So the labor cost is in purple, so we can see it's very less as compared to Australia, where it's very high. And it's even less, it's even similar in Brazil or even a bit lesser. But Brazil suffers with capex. The capex is very high in Brazil. On the other hand, India has a good manufacturing capability, so the capex goes down. Again, Australia being again a developed country, it has a high capex. Biomass feedstock is the cheapest in Brazil. Bagasse is grown, or sugar canes are grown in lot. Then second comes India, and Australia has the highest cost of production of biomass. Electricity, highest in Australia. Second comes Brazil, and the lowest is in India. So different factors would apply differently when we are talking about the same process. So we have the same process of ammonia production, only difference is different places and different biomasses. And you can see how different the economics could be. For India, I could produce ammonia for as low as around $700 per ton. It goes almost double, around 1,300 tons per day in Australia. A similar process, but a different biomass. The second thing would be, let's have a look at the capex or the capital cost breakdown. Again, as I told you, it's quite cheap in India, and it is somewhat higher in Australia and somewhat similar in Brazil. And also you can see the capex for different configuration. It's highest for the SMR case. The reason being, we need an extra reactor, an air separation unit to supply in nitrogen, whereas nitrogen could be supplied through the reformer in both the ATR and the CR. Both the gases coming in ATR, it's the air which has nitrogen. In the CR, it's the flue gas which again has nitrogen. But for the case of the SMR flow sheet, we need an extra source of nitrogen which is coming through ASU, and that has its own cost penalty. So we did a comparison with different studies for ammonia production from biomass, and we could say that we could achieve the same cost economics at a small scale, which people were proposing at around 1,000 tons per day. So that was an achievement. Normally, what would you expect as you decrease the plant size, the economics would go higher, as can be seen in the scales. But we achieved a similar kind of economics for different cases. The lowest one is straw, then comes Brazil for bagasse, and the highest one is for eucalyptus. And this was all because of the interventions that we proposed. So finally, life cycle assessment. What do you mean by life cycle assessment? Life cycle assessment means we quantify the emissions throughout the life cycle of the process at different stages. Now you grow biomass. You will need certain fertilizer, pesticides. We need to account for that. You transport biomass. There are trucks going to and fro. They will be going with biomass and returning empty. We need to take into account the diesel that goes into the trucks. Then we have the drying process. It would use electricity and heat. We need to account for that. We have the gasifier process, which would consume the different oils, charcoal, as well as the wet material. We account for that. We have the utilities. Either we will be using electricity from the grid or we'll be exporting it. We have the refrigeration unit, which would have its refrigerants. We have the different reactors, which would have different catalysts. We have the cleaning mechanisms, which would consume, again, different filters as well as chemicals. So we need to count everything to see if it makes sense to produce ammonia from the biomass. Are we doing any betterment to the society by adopting this strategy? So this is something we need to prove. So the process is like this. There are different categories of life cycle assessment or different indicators. The most common one is the global warming potential or the climate change. That is how much CO2 that you are leaving into the air. But is that all? No, there are many others. Like if I say these are the chemicals, this is just a small subset of chemicals that are emitted from any process. They could lead to 18 different categories. It would have ozone depletion, human toxicity, like are the gases that we are taking, are they toxic? Radiations, are there any particulates in the air? Ecotoxicity, acidification, are the water bodies getting acidified? Agricultural land occupation, are the agricultural land available? Ecotoxicity, eutrophication, the nitrogen content in the water, is that increasing or not? So we look at all the different categories, not just climate change. And then these categories can be also be clubbed together into a single score, which is called here, by using different normalization factors. So there are two ways of looking at the LCA result. One is at the midpoint indicators, where we can directly correlate the emissions to the indicators. Like we have the different gases which lead to global warming. We have different factors for that. We multiply them with the factors, add them, and we get the climate change potential or the global warming potential. And like this, we can also calculate the ozone depletion potential or ecotoxicity or eutrophication. So the path is quite well laid and you can easily correlate. But it doesn't make much sense to common people like you and me. So for them, they need a single score, whether the process is good or bad, as simple as that. So for them, we have all these things combined into a single indicator, which is called a single score. Again, there are three major indicators before that, which can be clubbed: human health, which means the human health in general. It's in a unit called DALY, which means disability adjusted life years. What is the normal years of a human being that is decreased because of any of these reasons? The second one is the ecosystem species. What is the lifespan of different species if it's decreasing? And the third one is the resources, the natural resources that we have, and it's in the form of dollars. So we can combine all of this to give a single score. Again, these kinds of things would vary with different locations and different time spans. But nonetheless, it's an easy way. But the values are different, it can vary a lot. Whereas in the midpoints, the values are much more concrete, but difficult to understand. So here is the global warming potential. Okay, so on the y-axis, what I give you is the kg of CO2 released per kg of ammonia produced, and these are the different factors. And this only relates to wood production from the three different configurations, which is SMR, ATR, and the CR. And we can see which are the different plant or different places where the emissions are coming from. And all of them, it's basically coming from electricity production. Now, the ammonia production would involve a lot of compression, and this energy has to come from the grid. And most of the electricity that is produced in India or in Australia is coal-based. So it has a lot of emission that is related to the production of electricity. So if I'm using electricity on the grid, I'm burning coal elsewhere. It might not, we not be able to see it, but it's being burned. So that is something we need to take into account. So the wood case have a good amount of electricity that is going in, and then we have fuel production in the CR case as well as in the SMR case. There is no fuel needed in the ATR case because we are burning a part of fuel gas. Then we have the transportation, the cultivation, and the different chemicals that go into it. If I look at a similar case for straw, the electricity production is even more because the electricity that we have in India is even more dirty. We are using coal, but that coal is even dirtier, and the efficiency of that power plant is even lower. So while I am having an emission of around 0.75 for Australia, the emission goes to around 1.2 or 1.1 for India for similar kinds of processes. If I go for Brazil, it's very less. So it's a huge jump. So electricity you can see here is less than 0.2, whereas it was more than 1 in India. The reason being, in Brazil, a lot of electricity is coming from hydro processes as well as burning of bagasse. So they are burning bagasse, using it to raise steam, and that steam is used to run turbines and produce electricity. As simple as that. So this was the global warming potential for 3 different feedstocks in 3 different supply chains. The next one comes ozone depletion potential. Now, I would ask for the attention here. Now I am looking at the different feedstocks at different places, but the same configuration, the ATR configuration, but it's wood, straw, and bagasse. And you can see that different factors lead to ozone depletion in different places. For wood in Australia, it's the road transport that is leading to ozone depletion. For India, it's the straw cultivation. A lot of pesticides go into straw cultivation, and they lead to ozone depletion. In case of bagasse, it's electricity production. So different factors can lead to different types of emissions in different places and different biomasses. So this is the point I want to impress using this study. The second one is the single score indicator. As I was talking about, I normalize all the calculations that I have and normalize that into a single indicator. So these are the 9 different cases: wood, ATR, SMR, CR, straw, and bagasse. So the maximum emissions are for India because we have the processes are not so efficient here. We have dirty electricity and whatever. It's somewhat better for Australia, but even they are not so good or not so better as compared to us. Brazil is way good than us. But if I compare this with the conventional ammonia production, which is going on average values, we are still saving a lot. The state-of-the-art ammonia production process would release almost 1.9 or megapoint per ton of ammonia production, but it can go as low as 1.5 for the worst case in SMR. So if I compare with the ammonia production facilities throughout the world taken average, all the 9 processes appear to be better. So we are saving in terms of emission, but that saving would depend upon the place, feedstock, supply chain, and a lot of other issues. So finally, multi-objective optimization. So what do I mean by multi-objective optimization? Now you all have heard about the word optimization. We all want to optimize the things that we do. But in multi-objective optimization, what we want to do is we want to come up with a Pareto front in which looks something like this, which gives us a graph, and all the values on this particular front are optimum. So you might be wondering, how can all of them be optimum? Yes, they are. They are optimum with respect to two parameters, which is the ammonia production cost and the CO2 emissions. So if I take a value here and a value here, so the value here would have a higher CO2 emission and a lesser ammonia production cost. A value here would have a lesser emission but more cost. So it's a sort of trade-off between the production cost and CO2 emissions, but all these values are optimum. So it's up to the user at which point he wants to work at. If he wants to have ammonia at a higher price and lower CO2, he can work at somewhere here at this point. If we want a lower price and higher emissions, he can work here. And how did we do that? We use certain genetic algorithms, and the name was NSGA2, which was a state-of-the-art algorithm. So the algorithm was something like that. So we run the simulation in Aspen Plus for a size of population of 100. We do a heat integration so that all the heat sinks and supplies are matched. We carry out a life cycle assessment and life cycle costing. Evaluate the objective function, which is minimizing both the production cost and the CO2 emissions. We rank a population, do selection, crossover, and mutation, which is very similar to the Darwin's theory of natural selection. The best solutions will go further, and the not so good will be left behind. And the generation goes on till we get the best results. So this is how optimization happens in concise. Let me try to explain it with the help of example. Say I have a first generation of solutions, and I'm trying to minimize both the global warming potential in terms of tons of CO2 released per ton of ammonia and the ammonia production cost in dollars per ton of ammonia. So my first generation of solutions will look something that is given in blue squares. It's widely scattered. The second generation would be somewhat better, or maybe like after 10 generations, like I see in the red. Then I run the simulation for another 20 generations. It appears to be somewhat again better. 30 generation, it becomes even more better. So this is how the solutions improve with time or with ahead with generations. So our aim was to get a precise curve, something beyond the purple curve, wherein we can get all the optimum values. And what are the variables that we do? We can change. So there are certain variables we need to change so that the optimum could be reached. So these were pertaining to both the gasification and the ammonia production process. So these are some of the variables that I state here. It could be the bed material flow rate, the steam that we're giving in the biomass, or the gas conditioning pressure, the air that goes to the ATR, or the temperatures. Also, we need to maintain the temperature in a certain range. Like the ammonia production, I want not to be less than 1800 kg per hour. We need a reformer temperature should not go less than 800 or more than 1100. There has to be a temperature difference between the gasifier and the combustion temperature for a good heat integration between the gasification and the combustion sectors. And once I give all these values, I can derive results, which look something like this. Okay. So these two graphs have a lot of information in them. So I will try to give as much as possible in the coming few minutes. So these is basically the 9 different cases, 3 different biomasses, and 3 different flow sheets. So this results basically pertain to India. These are for Australia, and this is for Brazil. Something similar here. The colors here dictate the ammonia production, and the colors here dictate the electricity import from grid. As you can see in India, we have huge emissions. It can go almost up to 1.9, which is similar to the ammonia production from coal or naphtha. But the price is way less. Australia, somewhere in between, but huge cost. The price is varying from 1400 to 1600, almost double than the conventional ammonia. Brazil, somewhere in between, but huge amount of emission savings. So this gives us a liberty to choose from different configuration. I won't go into much of the details, but one of the important factors that we're choosing in here, that we could use some amount of syngas for producing electricity. That means I'm using the hydrogen that I have for heating the steam, or like producing steam, and that steam can be used for producing electricity. So what I'm using, I am using some hydrogen which could be used for ammonia production for producing electricity. And that electricity that I'm using is going for ammonia production process, and I'm not importing much of. So the point here refers to when I'm using a lot of hydrogen for producing electricity, that means the ammonia production is lesser. But since I'm importing less electricity from the grid, I am having a low emission. You can see in here, the electricity import from grid is the lowest in here and the highest at this point. So it's more or less a trade-off between how I'm using my hydrogen for either for ammonia production or for electricity. If I'm using it for electricity, I can save a lot of electricity that is coming from grid, which is non-renewable and adds to my emissions. So this is how the different factors lead to emissions associated with a green process like biomass when we are looking at a circular economy approach. So this is where the circular economy comes into picture. And it could be having very different results for different geographies. Like you can see in India, some graph looks like this. For Brazil, it's very different. And Australia, again, it's very different. The slopes could be very different. And the nature of the curves could also, like the bending of the curves would be very different as well. So finally, we also came back that we can also come up with a global Pareto, which means if I want that this is the type of emission that I want for my ammonia production, this is the cost that I'm aiming for, probably I can produce a global Pareto and I can ask like, at which place in the world should I locate my plant? If I'm looking for very low emissions, probably Brazil is a best case. If I'm looking for very less economics, India is a good place. If not, like maybe somewhere in between, Australia might fit as well. So yes, so this is how we need to look at a bigger picture at the circular economies to come up with the sustainability of any process that is related to biomass. So next, we also need to check for the sensitivity in the cases. So herein I'm giving for the global warming potential or the CO2 potential for different parts of the world and for ammonia production. And we can, on the right hand side, I give that for biomass, the different biomass feedstocks as well as the different configurations. And I also show you the variability that is occurring. No matter what the variability is, we are reducing the emissions. It could be low in some point or high in some point. It is highest in the case of India and lowest in the case of Brazil, as I have reiterated in the past. So finally, conclusion. So we show you some systematic framework for for checking the sustainability of any product from biomass, which could be the fuels or chemicals. And we are using different variations of the process and doing a life cycle costing and a life cycle analysis. The different platforms have been used. It is like ANSYS Fluent, Aspen Plus, and then multi-objective optimization genetic algorithms, and the 3 different biomasses in 3 different places. Every like biomass, every place, every configuration has its own advantages. So you just can't say if this process is working in the US or in the Europe, it would work for sure in India, or the other way around. This process is working nicely in India, or even in among different states of India. If this is working in Andhra Pradesh, it will work in J&K. You can't be sure. You have to see the different processes. They have their different nitty-gritties, and you need to understand them and try to get the best out of it. So with this, I end my first presentation. Let me know if you have any doubts. So I'll take a break for 5 minutes. I would be happy to take any questions that you might have.
One question from Madam. The emission depends on the biomass gasification. Which biomass produces less emissions?
Sorry, can you repeat again?
Which biomass produces less emissions?
Okay, so like all of the biomasses would produce almost similar emission. It was the least for, as far as I remember, for the gas. I don't think I have a quantification here. Let me see. Okay, yeah. For bagasse, I have the emissions for different biomasses. So bagasse, it's 0.04. It's higher for straw, And it's again, okay, so eucalyptus has a least emissions, or almost similar to bagasse. So eucalyptus and the bagasse have almost similar emissions, whereas it's higher for straw. And the reason being a lot of pesticides that go into it, and the pesticides again are coming from fossil sources.
Okay.
Does that answer your question?
Any question from participant? No questions.
Okay. Okay, so let me take you through another study as well. I would be brief in this one. I know it's the last session and you might be feeling sleepy as well. So just like for the information, okay, let me see if my slide is visible.
Yes, sir. Visible.
Okay, great. So again, like in the earlier session, we had looked at production of sustainable chemicals. Now in this study, let's focus on sustainable fuels. And I'll focus on just one aspect of sustainable fuels, which is the supply chain. So here I'll talk about algal biorefinery. So what is an algal biorefinery? Now you might have heard about the green skine that grows in our ponds and different water bodies which are not used very often, and it's not a very good site to look at. So that is called something, and that is called algae. There are many species, and for that, but lately it has been observed that they have a huge concentration of oils, almost 70 to 80%. These oils can be extracted and can be used to produce fuels, which could replace the gasoline or petrol grade fuels or diesel grade fuels. But another advantage of these algae is they consume a lot of CO2. So they act as natural sequestrators. So this CO2 can be sourced from different sources as well, which have a concentrated source. So normal algae will grow in the pond, they will take CO2 from the atmosphere. But you can also supply concentrated CO2 gas, and the concentration of algae will increase because they now have more food. They will consume a lot of CO2 and grow. So they act as natural sequestrators. So a lot of research has gone into it. Can these natural systems be used for sequestration of CO2 from different CO2 sources? So what we will try to understand this in this other study would be, is it make sense to supply CO2 from different power plants? Now we have different power plants in our country, some of them coal-based or natural gas-based. Most of them are coal-based even till date, and they produce a lot of pollution. So we'll try to see if it is does it make sense to supply the CO2 from these power plants for the growth of algae. So, okay, let me do it full screen. Okay, so why make fuels from algae? First simple question. No, they require CO2 for their growth, and that means they are natural CO2 sequestrators. They use all the nutrients that are available in the water, so they don't do much of a eutrophication. They are biodegradable. If you accidentally spill it somewhere, it might have a not so good smell or fragrance, but it won't lead to any any environmental issues like the spills of oils that we read. It can be used in underutilized lands, like someplace in Rajasthan or maybe in the midlands of Australia, which don't have any purpose, because these creatures would only thing they need is CO2 and sunlight, and that is readily available in places like deserts. And the yield is almost 10 times. So their photosynthetic efficiency is more than 10 times than you would find in the normal terrestrial plants. Now, the CO2 supply to the algal biorefinery is a major source. And the CO2 requirements are responsible for almost 30% of the material cost. And it is also important to quantify the CO2 emissions with the production and transportation of the CO2. Now, the CO2 that you are using won't come without any burden. You need to capture it and you need to transport it, and that would consume energy. So this study tries to quantify that energy. Does it make sense to transport and capture CO2 to be captured by the algae? So we are running different scenarios just for CO2 potential, and the aim is to see what are the emissions associated with 1 gram of CO2 delivered to an algal biorefinery. And the CO2 seen as a final product. I don't take it as an emission. I am delivering 1 gram of CO2, and let me see how much amount of emissions I'm causing by delivery of that one CO2. So it's the emission associated with the delivery of an emission. So in that way, it's an interesting study. So just to give you another, a better understanding of the process. So this is our normal photobioreactor, which will be aiming for growth of algae. It's like a long mechanical reactor in which you grow the algae. The only thing you need is the algae, that's substrate, the light that is coming from sunlight, and the CO2 on which the algae would feed on. And finally, from the harvest of this algae, you can produce different oils, which could be of the range of kerosene, diesel, or even gasoline. And also, you can also aim for production of certain chemicals like nutraceuticals, fertilizers, and others. What we are trying to quantify is that if this CO2 is coming from power plants, what is the CO2 associated with this? So the methodology is we model all these processes in Aspen Plus, the similar software that we used in the earlier study. The point here is that now it's a steady state problem, but not in the sense it has a diurnal cycle. The algae will be growing or needing CO2 only during the day. The reason being the sunlight is only available during the day. So the process of photosynthesis can only occur during the daytime. So we only need to supply CO2 during the 12 hours of the day. So we need to take care of this. For the half of the day, we are supplying CO2 and we are not supplying CO2 for the half of the day. What do we do with the half CO2? If it's a specially built CO2 plant, we have to vent it to the atmosphere or we store it somehow. And it's a cradle to gate LCA study. So we took 4 different scenarios. The CO2 could come either from the coal-based plant, the natural gas-based plant. It could be a specifically built NGCC plant just before the biorefinery, and a biomass combustion plant. We are growing biomass, we are combusting it so that it could provide fuel for the growth of more biomass. So it's an interesting scenario in that way. And the aim of this scenario is we are having a 2,000 hectare facility, which is quite a decent size. And we are assuming that for the existing power plant, which is coal and natural gas based plants, and the biorefinery would be somewhere between 2 miles of the, or around 3 kilometers of this power plant. The standalone NGCC unit and the biomass combustion units are assumed to be constructed. So these kinds of plants won't be available and we would construct specifically for supplying CO2. So this is what the scenarios would look like. This is the first one where we are having a conventional coal-based power plant, which is producing electricity, supplying it to grid. The coal goes in. The CO2 rich gas comes in. We need a bit of scrubbing here and compressing it. We have a compressor for supplying it for 2 miles. And then we have another scrubbing just before the biorefinery. The second one is the natural gas-based power plant. But in this case, we need to do a carbon capture. The reason being the amount of CO2. The normal percentage of CO2 in the gas from a coal-based power plant would be around 13%, whereas it's almost 4% in natural gas-based power plant. So in this case, what you end up doing is supplying, if you're transferring it for a long distance, you're also supplying a lot of nitrogen, which isn't of any use. So it makes sense you use a CO2 capture system here, which has an absorber and stripper, which is a carbon capture system, get a concentrated supply of CO2 and then transport it for 2 miles. It doesn't make sense to supply a gas which just has 4% CO2 over 2 miles. It would have a huge economic cost to it. The third scenario is you build a standalone NGCC unit. But in this case, you also want to utilize this CO2 that is also occurring during the night. So what you do for that is you have a refrigeration system. So in the daytime, you just take the CO2 and supply it to the algal biorefinery. In the nighttime, you refrigerate the whole thing, store it, and then supply the whole thing during the daytime. So the CO2 supply is going only during the daytime, but in the nighttime, it's going in the daytime, it's directly from here and the storage. While in the nighttime, I'm just refrigerating the CO2 to liquefy it and then storing it. The fourth one is biomass. You can supply that gas again directly to the biorefinery. It has almost around 15% emissions. Yeah, just okay. So you have a biomass combustion flue gas, which you can supply directly by the burning of the biomass-based power plant, and you can supply that directly. The difference here is that while all the earlier plants were running on fossil fuels, this one is running on biomass, which is a green source. Remember the cycle? The cycle of the CO2? The CO2 that I release in here would be recycled in around 20 years, whereas the CO2 that I release from these plants would take millions of years. So this is what the results look like. It's most efficient for the least GHG footprint to use the CO2 from a biomass process, which is something intuitive. We are making use of that gas twice. And these kinds of systems are called BECCS, biomass energy along with carbon capture. And they're getting a lot of focus nowadays because you're using the same CO2 twice, making a much more efficient use than anything. And this CO2 can again then be recycled. So this is the beauty of the process. And then comes the coal-based power plant because you don't have any capture. Then comes natural gas-based process because you need to involve a capture, and that capture has its own losses, and that losses gets released to the atmosphere. And finally is the standalone process. So in the standalone process, you can say if I'm going to deliver 1 gram of CO2, I'm spending around 5 grams of CO2 for this process, which is not a clever decision at all. In case you are just spending 50% of the CO2 in the course of providing 1 gram of CO2, that's not a very intelligent choice. So this is what this study was all about. And again, the circular economy comes into the picture. You're using the end product of one process as a starting material of the other product. And herein I give the bifurcation of the emissions are coming from. I won't go into the details of this. And this is, and just to give you a total bigger picture how this process looks like, we have the coal-based power plant. I'm doing this. You have this scrubber supply over 2 miles, and then you have these PBRs which are running. And this is the process called hydrothermal liquefaction, which is subjecting this algae to around 200 bars and around 350 degrees Celsius. It will produce a biocrude, which could be refined to produce a fuel that you can use in your vehicles. And then it's a complex flow sheet, which I won't go into much of a detail, but this is what the process looks like. And if I look at the LC of the whole process, this is the point which we are aiming for. And there could be a huge variability in this, the CO2 supply. If I'm saying the total process looks very nice, a normal process which has a gasoline or diesel base would be somewhere here. So we are reducing the emissions almost 50%. And this reduction is basically because of the sequestrating of the carbon. And this could change vastly if we are looking for different CO2 sources. So this is the point that this study wanted to highlight, that different CO2 sources can impact the final emissions related to the fuel in a drastic way. And that's another way why we need to look at a circular economy where all the products of a process are used somewhere else they are going to cause trouble. So yeah, the CO2 supply from the biomass has the lowest process. So this is where the future lies in. And the standalone NGCC is something we shouldn't go for at all. And the fossil-based power plant is something that we can have a look, specifically in a country like India. So yeah, so with this, I end the other study as well. Let me know if you have any other questions. I would be happy to answer them.
Sir, one question. Did the quality of CO2 supply depends upon species of algae quantity?
Yes, it does. Different species have their own productivities, and based upon the productivity, they will consume different concentration and different amount of CO2.
Any question from participant? Thank you, sir, for your nice presentation on biofuel related with ammonia and your economical approach related with when we have used dual fluidized bed gasifier technology also we can use. So on behalf of Mechanical Engineering Department, ADIT, we'd like to express our sincere thanks to Dr. Arora sir for accepting our invitations and given a nice lecture. Thank you, sir.
Yeah. Yeah, thanks a lot for being such a nice audience. I believe you learned something new. In case you need any other information, you can contact me anytime. And thanks a lot again. With this, I'll leave the meeting.
Thank you, sir. All participants, now our next session on 25th September at 10 o'clock. Good day. Bye.